In this question, we are asked to calculate the pH of a buffer solution under 3 different conditions. In part A, for equimolar concentrations of a weak acid and its conjugate base. Part B, after the addition of 0.030 moles of solid sodium hydroxide to the solution in part A. And C, after the addition of 0.030 moles of hydrochloric acid to the solution in part A. The starting point here is to write a balanced chemical reaction for the reaction between acetic acid and acetate. And we know that we can set up an equilibrium reaction by reacting acetic acid with water, which will exist in equilibrium with its ionization products, HCl+ and acetate. Next, we'll write the initial concentrations of the species that we're given, and we know that we're given initially 0.60 molar acetic acid. Water is a pure liquid or a pure solvent, so we just put a line through it. We don't start with any HCl+ in solution, and we start with 0.60 molar acetate. Here we can recognize that we have a weak base and its conjugate acid, and so we can tell ourselves, aha, I have a buffer. Next, we'll write the expression for the Henderson-Hassbach equation, which will allow us to calculate the pH of our buffer system. And we see that pH equals the pKa minus log of Ka divided by Ha. Here, we can put in the value for acetic acid, as well as the value for the acetate ion. Next, the only thing we need is the pKa, and in this case, we're only given the Ka, but that's okay because we can calculate the pKa from the Ka using this equation, where pKa equals a negative log of Ka. And next, we substitute in the value for our Ka, acid dissociation constant, which is 1.8 times 10 to the negative 5. So plugging this into our calculator gives us a value of 4.744. So now we can just plug this value in here, and we have the pH equals 4.744 negative log of 0.6 molar divided by 0.6 molar, which is the concentration of acetic acid. We'll see that 0.6 molar divided by 0.6 molar gives us a value of 1, and the log of 1 is 0. So in this case, the pH equals the pKa, which is 4.744, and rounding gives us a pKa of 4.74. In part B, we are asked to calculate the pH of the buffer from part A after the addition of strong base, hydroxide. So we can imagine that the reaction would be between the hydroxide and the acetic acid. And so the balanced chemical reaction for this would be acetic acid plus hydroxide produces acetate plus water. Next, we'll fill in the initial number of moles of each of the species, and this gives us 0.60 moles of acetic acid, which is what we had started with, plus 0.030 moles of hydroxide, which is the hydroxide that was added to our buffer solution, and we have initial concentration of 0.60 moles of acetate, which is also what we had started with. Water, of course, is a pure solvent, and so we just put a line through it. The change in concentration for this will be determined by the amount of hydroxide, since in this case, hydroxide is the limiting reactant. So the change is going to be negative 0.030 on the reactant side and positive 0.030 on the product side. Next, we'll just add up the columns, which gives us a final number of moles of 0.57 moles of acetic acid. We can see here that when we add up the hydroxide, we get 0 moles of hydroxide, and we have 0.63 moles of acetate. So here we see that we have a weak acid with its conjugate base, and we can say to ourselves, aha, a buffer. So we know that we can calculate the pH of a buffer using the Henderson-Hassbach equation, where pH equals a pKa plus log of A minus divided by the log of Ha. And here we see that 0.63 moles is the number of moles of conjugate base, and 0.57 moles is the number of moles of acid. The next thing we need is the pKa, and that was calculated in part A of the problem. And so substituting in all the values, we have the pH equals 4.744 plus log of A minus, which is 0.63 moles, divided by the log of HA, which is 0.57 moles. Now, here you'll notice that the Henderson-Hasselbalch equation actually specifies the concentration, but here we've put in the number of moles. And the reason that this works is that both HA and A minus are in the same container, so therefore have the same volume. And so the volumes would just cancel on the top and the bottom. So now we can put these values into our calculator, and this gives us a pH of 4.79. In part C, we are asked to calculate the pH of the buffer solution from part A after the addition of H3O+. And so here we can imagine that H3O+ reacts with acetate in the reaction as shown here. So we have acetate plus H3O+ produces acetic acid plus water. And next, we're going to write the initial concentrations of each of the species. And we see that we start with 0.60 moles of acetates, and to this we add 0.030 moles of H3O+. And of course, we also start with 0.60 moles of acetic acid. Now the change in this case is going to be determined by the limiting reactant, which is the amount of H3O+. And so we can see that we have negative 0.030 on the reactant side and positive 0.030 on the product side. Now adding the columns together gives us 0.57 moles of acetates, 0 moles of H3O+, and 0.63 moles of CH3COOH. And so we can see here that we have a weak base and its conjugate acid. And we can say to ourselves, aha, a buffer. And this is useful because to calculate the pH of a buffer, all we need is the Henderson-Hasselbalch equation, which states that pH equals to pKa plus log of A minus divided by HA. So we can just substitute the values into our Henderson-Hasselbalch equation, and we'll see here that the concentration or the number of moles of HA is 0.63 molar, which would go here in the denominator, and the number of moles of its conjugate base is 0.57 molar, or moles, which again we can put here in our equation. The last step is to write down the value for the pKa, but again this was done in step 1, or part A, and so we just substitute in all the values and we get the pH equals 4.744 plus log of 0.57 divided by 0.63. And plugging these values into our calculator gives us a pH of 4.70.